Hello again, physicists. Today, I bring to you a new topic called uniform accelerated motion. So before we get into what uniform accelerated motion actually is, we need to talk about what is acceleration itself. Verbally, our definition would be that acceleration is a change in velocity. And as an equation, generally speaking, acceleration would then be a change in velocity, delta v, divided by a change in time. So let's take a quick moment before we get into conceptually how acceleration will apply to us graphically and mathematically. What are the actual units for acceleration? So I'm going to do a quick dimensional analysis on this formula over here. Okay, so the units for acceleration will be equal to the units of velocity, meters per second, divided by the units of time, seconds. So if I rewrite that so it looks like this, it becomes more obvious to what we'll have to do here. When we're dividing by something, we know that we keep the first thing, we're going to change the division to multiplication, and then we're going to flip the second thing that we're dividing by. So this will become meters over seconds times 1 over seconds. And this means that when I multiply, I'll have meters in the numerator and seconds times seconds, or seconds squared, in the denominator. So this right here is my unit for acceleration, meters per second squared. As a final note, I just want to point out that, like displacement and velocity, acceleration does have direction associated with it. So you can have a positive acceleration or a negative acceleration, and we will refer to negative acceleration as deceleration. Now that we've taken a little bit of time to identify what acceleration itself is, we can get into this special type of motion called uniform accelerated motion. And this will be motion where the acceleration of an object is constant, or it is not changing. Some examples of uniform accelerated motion include a ball rolling down an incline, which we actually did in class when we were collecting some data. You could be falling from a plane, or really any falling object in general would be undergoing uniform accelerated motion. And if you've ever been in the car and you slammed on the brakes, that would also be an example of uniform accelerated motion, where you would actually be decelerating. So now we're going to take a look at, graphically and in terms of an equation, and conceptually, what does uniform accelerated motion actually look like. Let's start with a graphical interpretation for uniform accelerated motion. When I had you in class collect data for that ball rolling down the incline, you were actually collecting data for an object that was undergoing uniform accelerated motion. And we saw for our position versus time graph that the relationship between the position of our object with respect to time was nonlinear. It was actually, we found out that the ideal fit for our data was quadratic or parabolic. Thus, when we looked at the velocity versus time plot, we saw that for this object, the velocity was changing. In fact, it was increasing, and it was a linear relationship between the velocity and the time. So what this means is that if we wanted to take the slope of our velocity versus time plot, our units would actually be units of velocity divided by units of time, since I'm doing rise over run. And we saw in the last slide that dimensional analysis will tell us that that would come out to meters per second, or units of acceleration. So the slope of a velocity versus time graph will actually give you the acceleration that an object is experiencing. And it'll just be a constant, it'll be non-changing. So in uniform accelerated motion, if we did an acceleration versus time graph, it would just be a flat line because our acceleration remains constant throughout. So just keep in mind this pattern of for position versus time, velocity versus time, and acceleration versus time for when an object is undergoing uniform accelerated motion. The last thing we did in class on Friday was that we looked at, okay, well, now that we have these plots for something undergoing uniform accelerated motion, let's see if we can create a mathematical model or a fit for each of these graphs. We saw for position versus time that our fit would be quadratic in nature, which meant that we needed to have some sort of equation where we had a constant multiplied by time squared. We then had a second term that would be another constant multiplied by time, and then our last term just being a constant itself. And it turns out that the way we would read it ultimately is if we wanted position as a function of time for something undergoing uniform accelerated motion, it would be the initial position of the object plus the initial velocity of the object multiplied by the current time plus 1/2 the object's acceleration multiplied by that same time squared. And keep in mind that the initial velocity as well as the acceleration in here, these will just be values, especially the acceleration. Since it's uniform, since it's constant, that means for every scenario in uniform accelerated motion, the acceleration will just be a number. Alright, and then when we looked at the velocity versus time graph, we saw this is a linear relationship, which means it'll follow the general form y equals mx plus b. And in this case, when we translated that into terms of symbols we use in physics, it would be that the current velocity of the object is equal to its initial velocity plus its acceleration multiplied by the current time. And then the only real extension we can go from here in terms of any mathematical representation is if we look at acceleration versus time, we're just reminded that the acceleration is constant and that it will just be a number. So there really is no function, no expression mathematically for the acceleration of an object when it's undergoing uniform acceleration. Alright, the last thing I want to point out to you happens to be this little equation down here. This is what's called the time-independent equation. And basically what you do is you solve for time in one of these two equations up here, and then plug that solution into the other equation. And this is what you're left with. This is a way to express acceleration, position, and velocity without any time dependence in it. And the equation would be read as the current velocity squared for the object is equal to the object's initial velocity squared plus 2 times the object's acceleration times its displacement, or its change in position. So there you go, 3 equations for how we can mathematically express quantities related to uniform accelerated motion. The last thing for today is I want to show you a visual representation of what acceleration and deceleration actually would look like. So we're going to focus on the top half of this example for starters, where I'm showing an object undergoing acceleration. Each hash mark is representing an equal amount of distance, and each dot represents our object 1 second further into its motion. So as you can see with our top example, the object is gaining a significant amount of displacement from 1 second to the next second. The first second, not a large amount of displacement, but during the next second, a little bit more displacement. The second after that, even more displacement. And the second after that, an even greater amount of displacement. And that's because with each passing second, the object's velocity is changing. In this case, it's increasing, and therefore it is undergoing acceleration. Now let's flip the script. Let's look at a case where an object is actually seeing its velocity decrease as time passes. In other words, deceleration. In this case, the object will initially start out by displacing itself by quite a bit in the first second, but then as time passes and we go into another full second, it doesn't displace itself by as much, and then with each passing second, it displaces itself by less and less. So in this case, the object's velocity again therefore must be slowing down, thus it's undergoing deceleration. Alright folks, so we're going to spend a fair amount of time in class just analyzing and making sure that we're comfortable with interpreting uniform accelerated motion in multiple ways. So with that said, until next time, physicists, until next time.